Yeah, so we'll today just talk about, just one second. Yeah, today we'll talk about what is really useful in the lab. So exactly what we are supposed to do finally, like the earlier class, we were kind of discussing more on the bigger picture of why error is important. So basically, this is a set of notes that I used in, like I gave a lecture, very similar lecture on error analysis in the MSc physics course. So I'll just use that notes in case if you go out of connect, at least the notes are there. And please, yeah. Any questions? Can you hear me?
Yes, we can.
Okay, yeah. So yeah, please feel free to stop me at any point. So we'll basically, like when we actually analyze the data, when we take the data and when we write the report, project report and so on, we'll actually be facing two kinds of scenarios, which I'm calling case 1 and case 2. Case 1 is kind of the simple, straightforward scenario where you have taken n data points, x1, x2, xn, and you are basically asking the question. Actually, it's, if you actually appreciate the question is kind of hard. That, for example, if each of these data points are actually taken in very similar situations. So suppose I'm taking it from an instrument, which actually there's a fluctuation in the data, as we were talking last time. And so the data might actually be taken all from a distribution, which has for example, a Gaussian distribution. So this is basically, the mean and the standard deviation. And the probability of getting a particular value of xi is just exponential minus xi minus mu divided by sigma whole square, and so on. So given this, you see that as I take the first one, it's px1 is the probability, then px2. So finally, when I have a set of n data points, the total probability of getting that data is actually like product of all this, how that probability distribution looks like. And for example, things where I might actually take the data points and do a weighted sum. This is something we actually do all the time. For example, last time we were talking about, we might calculate the mean, xi, exactly a weighted sum. And we might ask this quantity actually is the sum of all this n data points. What is the distribution of this this mean? So last time we talked about this a little. So this is a very fundamental question. Please make sure that you understand this question, that it's actually set we are creating of n random variables, and with this n random variables we can create other functions which are also random variables, like a sum, a weighted sum, and so on. And what are those distributions? So this is one kind of question we'll be interested in with the data points. That's what we do. The other is actually a little bit more involved, that like let's say we have two such data points, xi and yi, so maybe the voltage and current, and we have a theory that takes this xy, combines them to create a new quantity z. And now we are saying that, we know the distribution of xi, or maybe we have some assumption regarding the distribution of xi and distribution of yi. What is the distribution of z? What is the error in z? Or rather by error, I mean, what is the standard deviation of z? What is the mean of z, and so on. So these are the two kinds of questions. In fact, like what we'll today talk about primarily is this error propagation formula, different forms of that, how the standard deviation of the combined measurement looks like. And there actually you will see in your optics course also, we'll often be using this different measured quantities and construct new quantities based on a theory and so on. So any questions up to this point? So if not, like these are like, and just it's the bigger field. Hello? Yeah, this is a much bigger field, of measurement theory. So here, actually, there are two very important questions. Someone's microphone is open on in the back. There's a background noise, no? I think now it has stopped. Okay, great. Yeah, so
yeah, maybe I can request everybody to shut off the microphone.
Yeah,
other than Saikat, of course. Yeah.
So there are two very important questions. These are very big questions, and one can spend like 2-3 semesters on these. But let me just mention this question so that you remember. One is that what is the probability distribution of this derived quantity Z? Like I have measured 2 quantities and I'm deriving a third one, or like n quantities and deriving a third one. So when you're asking this question that what is the distribution, what is the most likely distribution, or what is the sensible distribution of this combined quantity? So when you're asking such questions, this is what is called this theory of inference. There are these concepts of entropy that comes in here, and there are this like laws of maximal entropy, and that gives you a distribution. All these very beautiful theories, but we'll not go into that at all. So that you are just aware. The other kind of question that people ask are that suppose I know some underlying distribution. I have used very carefully theory of inference and got the distribution, like underlying distribution of this derived quantity Z, or this weighted sum of all these random variables. So given this distribution, now I have a new set of data xi, and I have told that you have a distribution, like the underlying distribution is, let's say, a Gaussian distribution or a Poissonian distribution with some parameters. I have this data in hand. How well I can use to estimate these parameters, So this is a very fundamental question that, I want to measure acceleration due to gravity. I want to measure fine structure constant. I want to measure a wavelength of a laser source. How well I can measure, given that I have a set of numbers, maybe like 20 numbers, 25 numbers. What can I do with those numbers? How can I combine them to actually get the best possible estimates of this parameter? So when you're asking this question, this is actually a question of theory of estimation. And so there are this turns out to be a field of information theory. There are these ideas of Fisher information, which kind of quantifies that given your data, how well at all you can measure these estimates and so on. So this gets very deep, but we'll not go into that. Just make sure that, these are the questions. I'll send these notes after this. So one very important point, since we are experimentalists, we'll be measuring. So one very important point to remember is that as experimentalists, we never measure really probability distribution function. So this PDF stands for, let me write it down. So this is basically probability distribution function. Function. So basically, like any kind of distribution of a continuous variable, like a Gaussian distribution or a Poissonian distribution, are basically PDFs. And as opposed to if you have discrete variables, you call it like probability mass functions, for example, binomial distributions and so on. So whenever, we are never measuring either PDFs or PMFs, probability mass functions. What we measure are actually moments, So this is something you might already be familiar with your, with your introduction to probabilities when you did it in your first year maths courses. So we basically, actually in the lab, will be measuring things like the first moment, which is kind of a mean of your data points, maybe the second moment, and so on and so forth. You can go on and on, so the third moment is skewness. And in general, when you don't know anything, a system might actually have a very arbitrary probability distribution. It might not be Gaussian at all. It might have many, many parameters, multi-parameter system. You might need the mean, this thing, but you also might need some sort of a median, a second peak, all these different informations, higher and higher order moments. And that's what you do as an experimentalist. You basically measure these moments, and from there you infer what your probability distribution is. So I think this is, I'll actually give the notes. I'll just kind of state that all the students are experts in probability distribution. One part of probability distribution which really helps to understand data, and this whole theory of inference, one property of probability distributions, which is this moment generating function. It's a function of a parameter, t. T is not necessarily time, it's just some parameter, it's this usual mathematical trick that you stick in a parameter, you calculate everything and put the parameter to 0. And it's basically expectation value of exponential of x, your random variable, times this parameter. So for example, if you have discrete variables, so then you basically have just px times this quantity ext. If you have continuous variables, PDFs, then you have this px dx times ext. So this is a very useful quantity moment generating functions, because of the fact that you see that this exponential expansion of exponential ext gives you this x to the power n, which is like the the average only acts on the random variable. Nothing else is random here. T is a parameter, n is an index. So basically the average goes on x, and this just becomes the moment of this function, which is very nicely a property of the exponent, that if you take the nth derivative, you basically get the nth moment. Just 1 second, someone is knocking. Hello? Hello? Hello?
Yes, sir.
Yeah, Saikat. Yeah, go ahead.
Yeah,
Go ahead.
I'm still there. Okay, yeah. So this is just a mathematical trick, but very useful for thinking, because you see that this parameter gxt seems to be containing all information on the probability distribution. You just want this moment, and if you want to think in terms of moments, you just take the nth derivative, and that will just give you the nth moment. So it's very useful. The 0th moment being just 1. So this is just certain things to show. It's kind of another very beautiful property of this moment generating function, that if you take this log of these functions, then the derivative with respect to t, the first derivative actually of the log function gives you the mean. The second derivative exactly gives you the standard deviation x minus mu x. It's very beautiful. The third derivative gives you exactly the skewness, but it kind of breaks down after that. It doesn't work for the fourth derivatives and so on. But till third derivative, it very beautifully kind of comes. Work out. You can, like, these are just things you can work out for binomial, Poissonian, just to get used to that. So why I am talking on this moments, so let's consider this particular example, which is basically, like the first example being just calculate for all these known distributions, e to the power xt average. But the second example, usually we don't notice. So consider a linear combination of random variables, which is your data. So you have gotten like 23 data points, and you basically combine them to form a quantity. For example, you can actually calculate the mean. Last time we were talking of this, that you might be calculating the mean, which is also a random variable, or you might actually be doing any weighted sum of this n data points that you have gotten, right? And you are asking the question, this is the question I was kind of hinting. It's a very important question, and right now we'll see the first usage of this question. So we are always interested in this theory of inference. We are asking the question that what is the moment generating function for this variable, new variable, which is a combination of all my data points. Like this might be towards calculating the acceleration due to gravity or something. So what is the distribution of Sn? You remember last class, people who were there, we are talking of this distribution of the mean. Exactly in that spirit, this is a more general formulation. So I'm asking what is the, background noise. So basically, what is the moment generating function of this entire thing Sn, the linear combination? So this is very straightforward maths. So you are basically asking what is this? So it is actually, you can expand this. And since the summation is in the exponent, so this just becomes product, n products of this xi's. But xi's are actually drawn from a distribution which has its own moment generating functions. So you see that the total moment, it's kind of a very interesting thing to remember, that I am asking that what is the distribution of this quantity mean that I'm calculating. It's actually the product of the moment generating functions of each of those. So for example, same function I'm drawing from, so this would have just been gx, AIT. Yeah, if not, a few things you can actually observe. For example, the first moment, the first moment of this larger quantity, the sum actually is just the same weighted sum AI times the moments corresponding to each of them. So for example, let's take this again, go back to the simplest case. You're taking data from the same distribution. So all the AIs are same, 1 over n, the same weight. You're calculating mean, so the X bar mean you see is 1 over n times summation over all the moments of the individual distribution, which is mu. So n mu divided by mu. So it's just mu. So they're just basically telling you the moment of the total distribution is actually the moment of that mu that you are after, the estimation of the parameter. Similarly, the second moment actually, yeah. So the second moment is kind of interesting. You can calculate. I'll give you the notes. So, but you can go through it. So like the derivatives, both of them act on one. And then it, like one acts on this one and the other acts on this one. So you have, and if you the value, it's a little non-trivial. You find that the second moment, or the root mean square deviation or standard deviation of this new quantity xn is actually not just the weighted standard deviation of sigmas, individual ones, but it's actually ai squared times sigma squared I. It's kind of a little non-trivial. You see, the first moment was ai mu I. If you're mathematically thinking, you might say, oh, it's obvious ai square sigma I square. But if you think of it, it's not trivial. Any questions? So why we are doing this collected thing? Because let's go back at actually collecting the same example. I'm coming back again and again. We have taken n data points, and now mean just now I talked about x bar is just n mu divided by n, so it's just mu basically, but the standard deviation or the variance of the sample mean is ai square sigma square I, so all I'm drawing it from the same sample, so all sigma xi are equal to sigma. So if I do that, so it's sigma square coming from all of them being equal, so then 1 over n square is coming from the fact that ai is 1 over n, and summation n is coming from this. So it's actually, you get this like $1 million expression, that finally the variance of the mean, or the distribution, total distribution as the mean, if you're calculating, is actually sigma square over n. So basically, the conclusion, we'll actually just now do an example to clarify this as much as we can. So each data point you were drawing from a sample, and each data point had a variance of plus minus sigma. Now you are actually taking them, combining them to form like n of them to form a mean, and you ask the question. It's very important to realize that the sample variance is still, sigma, if you calculate xi minus x bar squared. But when you actually calculate what is the mean variance of the mean, so x bar minus mu whole square, so that's actually sigma over root n, right? So the number you have calculated x bar, how much that is varying, so that is going down with the number of data points. Any questions up to this point? So this is also famously known as, it has a name, like it has many different names, this behavior 1 over square root of n. Sometimes it's in theory of measurements, it's called the short noise limit, or I think even more famously, it's called the standard. I was kind of trying to avoid this name, standard quantum limit. Actually, like the only part where the quantum comes in, so it's also called SQL. I have used the term central limit theorem. If you guys have done in statistics, so this is a random processes. Every data point is a random pick. It's like a random walk, and you are asking like, what is the variance of my sample mean? And that's basically 1 over square root of n. So actually, let me, yeah, any questions up to this point? Am I still there?
Yes, sir.
Yeah, yeah, yeah. No,
Yeah.
no issues.
So yeah, so basically, like you can actually go more thoroughly, the sketch for the proof of the central limit theorem, just the way I did it just now. So actually, the central limit theorem by itself says a little more than this. It's kind of quite striking. It says that suppose you are actually constructing this X bar out of this n data points, so this is a random variable constructed out of this. So this is the kind of the probability mass function or distribution function or the moment generating function, which is a product of all of this n ones. So that's the total, the distribution of X bar. So you can actually do something very simple. You actually ask that how does Gx bar look like when my n starts getting very large? Like when n is in the asymptotic limit, when n is a very large number, how this looks like. So you would have said that, oh, it's a product of many probability distributions, so it must be becoming very small. But also you see that this t scales as 1 over n, so it's non-trivial. So you do an expansion for large n. So when you actually take the log on both sides and you expand, you find that when you expand this log for 1 over n, you find that the first term is just the first moment times t. That is what you have expected for this. The second moment goes as sigma square over n, exactly the result just now we had, t square. The third moment goes as 1 over n square. So when n is large, so for example, when n is 10 or 100, let's say 100 or 1000, you see that this number is 1 over 10 squared or 10 to the power minus 2. This number is 10 to the power minus 4. So this is very, very small. And it's actually the moment you observe this, it actually tells you something very interesting. So we are looking at the distribution again. I'm talking of only one example, the distribution of this means, and what we find is that this distribution, how does it look like? There's a big clue that the moment generating function is suggesting that when n is large enough, there are only two moments remaining. The first moment is the mean, and the second moment, which is actually going down as 1 over square root of n as n is getting larger, is the standard deviation. All other higher order moments are falling down really fast. So for all practical purpose, we can take them 0, which actually states a very, very important result that actually for any distribution from which you're drawing these data points, if you take enough large number of them, all these distributions, no matter what you started with underlying distribution, Hello?
Sir, you stopped sharing the screen.
Yeah, I think something happened. So basically, what I was trying to say is that it becomes Gaussian, but I think something. I think my broadcast stopped.
No.
Hello, can you see my?
Yeah, now.
Yes, sir.
Now we can see it. Yeah.
Okay. So basically, it's a strikingly amazing result. It's basically saying that no matter what you're drawing from, all distributions together, like when n is large enough, starts looking Gaussian. The only catch is that the distribution, the parent distribution from which you are drawing this exercise, they need to have first and second moments. As we were talking about last time, that there are probability distributions like Lorentzian or Cauchy, for which there is no first and second moment. In that case, the central limit theorem doesn't work. Otherwise, whenever any probability distribution has second and the first moments, you basically learn that all of them start looking Gaussian. Any questions? Yeah, so it doesn't hold for this kind of things. Any question? Yeah, if not, let me go into this example, So this example is a very straightforward, simple, yeah.
Yeah, so there are at least a few comments, and people are saying that, I guess, Y20 batch, they have not done the any stat course yet. And so this distribution and the related stuff kind of not making much sense to them. So if you can,
probability distributions you have done, no?
So no, yes, they're saying if you could share some material or book that they can follow later, that will be useful to them.
Yeah, of course. I cannot believe I have not shared that. I'll send you that.
Fine. And then whatever link Saikat says, I'll put that on the course webpage.
I'll actually share the PDF. It's not for commercial purpose. just for academics and education. So I'll share that PDF. Keep it to yourself, but that is a great book. Yeah, but otherwise, I'm talking of probability distributions exactly in the same sense of that of high school. If you remember, like we did probability distributions for binomial distributions, Poissonian distributions, Gaussian distribution. So for example, this is actually a distribution which is characterized by just mu and sigma, and this will just look like square root of 2 pi sigma minus x minus mu over sigma whole square, right? So it's basically saying that in my x-axis, it's a continuous variable. If I want to ask that I have gotten a number xi from my data, a certain number which lies here, what is the probability that of getting that xi, and you basically replace your number by xi, and that gives you the probability. So this is the only thing you need to know, and then after that it's just like some simple maths. So let's take this example, right? So this example is basically that you have some particles or some counts, or maybe you're some digital turn light on and off, or maybe you're counting, you're doing some interference fringe experiment, so you have some sort of set of fringe, and you're counting a set of numbers, 1, 2, 3. In this case, you see that these are particles arriving at a detector. So this is a detector. Particles are all coming in this direction, and you basically say that starting from time t1 to t2, or rather t1 to t2, I'll count for 10 seconds. I'll wait for 10 seconds. And within that 10 seconds, I'll see how many events are passing. So there might be here 6 particles, or like 10 fringes, whatever, like the discrete things you're counting. They are random, uncorrelated events. So you basically define a time mill, and you count, and you get a number x. Let's say like you get the number 6. Right. So that's your measurement. You have waited for a certain time, and you have seen 6 events, maybe 6 photons falling on your detector, 6 electrons, 6 buses going past your bus stop. That's your number. And also someone told you that these particles are basically completely random and uncorrelated. And if discrete events which are completely random and uncorrelated, this I think you probably in your high school you did this. If they are truly uncorrelated, then you always get a Poissonian distribution. So that the Poissonian distribution, basically its mean is sets the standard deviation. Square root of the mean is the standard deviation. You have only one data point in effect, so you have a number 6. So you basically say that you state the result that your measurement is x, 6 plus minus square root of 6. So this basically tells you, this is an information you're gathering from the fact that you have been told that it's a Poissonian distribution, but it's not really a measurement, you see. So this is the first case. This is the worst possible bad measurement. Like you can actually improve this a little bit. So this is the case 2, where you actually say, I'll do a little better. I'll actually, this is my time bin, but I'll actually now repeat this like n times. So I'll have like n such time bins, so repeating the above process for n bins, and each of these bins I get a count xi, and I have n such counts, I goes from 1 to n. So what can I calculate from this? I can actually add up these numbers and calculate the mean. And I can also calculate the standard deviation from the mean. Sigma x square is xi minus x bar square. Right. So this is all calculated from my data. You see that this is what is being used to calculate the standard deviation and so on. So how do I? So these are usually called the sample or population. I think population mean and population variance. You just use your data to construct these things. And what do you state the result? You basically say that my result is that I have a mean x bar, and I have a standard deviation plus minus sigma x. Now you're doing a little better job because you have n data points, and you actually see that sigma x is actually, like, instead of just guessing from Poissonian process that it was square root of x, you have actually calculated the number. This can be anything, like you actually have the number, But, hello?
Yeah, I think it stopped sharing again. So.
Again stopped, Yeah, somehow we do not have a very good internet connection.
Maybe you can switch to the, I think I'm also on my data, mobile data. So
Maybe I should have. Yeah.
there is some connection problem, it looks like.
Yeah, I think it's just like this one is just going up and down.
Yeah, we can see your screen now, huh?
But it seems to be very slow. Yeah. So, so basically, how do you state the result? You basically say that you have x bar plus minus sigma x, and the sigma x is actually calculated the number. But I still now see that it's not updating. It's frozen again. Stopping the broadcast. And now it seems to be better slightly. Yeah, so you state the result x bar plus minus sigma x, right? But now the question is that this is where the issue comes in, that you know actually a little more. You know that this x bar, so this was your like data variance, standard deviation, but x bar, just now we did this analysis of the central limit theorem and so on. So x bar, if I think of it as a random variable, then x bar actually has a standard deviation, which is sigma x divided by square root of n. You know this, but there's no way you can actually verify this. You see? There's no way you can verify. You are basically like, this is a statement as good in this case as the earlier guy was making a statement that, oh, I know that my standard deviation is plus minus square root of mu, but there's no way I can verify. It's identical scenario here. You see that you know that your variance of your standard deviation is square root of n, but you cannot verify. So you can now do a third thing. You can actually do a little better. So this is case 3. You expand the experiment further, So now you collect m such data points and calculate the mean for each of them. Please stop me if it's not becoming clear. This one little example, if you keep in your head, it will always be have clarity. So you have now calculating. You have calculated n such bins before. Now you have taken m such n bins. And you are calculating the means. So you now have m means. And each of these means are calculated from n such data points, and there are m of them. So now you see that you can actually now calculate a mean of means, So you can actually calculate mean of x bar, which is 1 over m, j equals 1 to n, x bar j mean. Last time someone was asking what is the mean of standard deviation of mean. So this is what it is. So x bar j, the means corresponding to each of your thing, minus mx bar, and basically this is your sigma x bar. So you see that this is your mean plus minus, this is how you code the result for this set, that this is my mean, though it is actually the mean of the means that you know from your partitioning, and this is the standard deviation. But if you have done it well, and if your m and n are large enough, and like experiments are like they are very they're very kind. Nature is very kind, so n doesn't need to be very large. Like 10, 15 is already large enough. So if you have taken large enough n and m, you should actually find. Hello, Arton, your microphone is on, I think. Yeah. Okay. So you see that basically your variance of standard deviation is actually sigma x divided by square root of n. So this you can verify, because you have all of them. You have sigma x, and now you have sigma x bar. So in this particular case, you can actually verify. But you also need to understand that you have not gained anything. It's just different ways of looking at the data, because you can actually look at the entire variance, and that's actually sigma x bar square over n. This is something you know. right? So now you see that now you are saying that this is the mean. This is sigma x bar is 1 over square root of n, but mean has a standard deviation, and that's actually like, just peeling an onion. It just goes on and on. This you cannot verify, but you know that this is sigma x bar over m, which is sigma x squared divided by mn. And the same result you would have gotten if you would not have partitioned this data, but if you would have taken m times n, then you construct a new quantity y, and your y basically can calculate the standard deviation and exactly find this simulation. Any questions up to this point?
Yeah, sir, how do you decide where do you stop here?
You don't stop. You are not stopping anywhere, you see. It's actually like, well, if you really ask where you stop, the stopping as an experimentalist when you're taking data is happening how much m and n you can afford, right? So this is, like you may be forced to stop here, right? You may be like, like for example, if you are actually making a theory of multi-universe and so on, and you have only one universe, so basically X is one, and you really cannot do any further experiments or comment on anything. So you might be forced to stop here, or you might be forced to stop with n at 10 or n at 100, or you can add like further n's. So it really depends on where you stop is how far you can go. So this is actually part of a measurement theory called resource theory. So exactly this question that how far do you go depends on what resource you have. So resource as in how much time do you have? How much energy do you have? How much money do you have? Like, can you actually really repeat an experiment for a billion number of times? If you can, great. You basically go closer and closer to the truth.
So suppose instead of arbitrarily trying to reach as like, let's say you have n resource and you spend all n of the resource into doing this experiment. Instead of that, can we like set a barrier? Let's say, basically, is there a way to quantify how good each of these things are? I mean,
yeah, so that is the theory of estimation. That's exactly the question you asked, basically. So you asked that it's not a question of how much resource I have, but if I know as far as given n, is there a limit of how good of the sigma x bar is? Is there a way I can actually, like by using the same n, can I do better than this? These are the kind of questions you ask in theory of estimation. And it turns out that there's something called a Kramer-Rao bound. If you're just asking for the sigma, the limit for the standard deviation. So there's this Kramer-Rao bound which sets the bound. And it turns out that that's exactly 1 over square root of n. It's kind of very interesting that you cannot do really better than uncorrelated events. Like classical correlation doesn't help you at all. But interestingly, like if you somehow have quantum mechanics and systems, these n systems are quantum mechanically correlated, then it turns out with the same n, instead of 1 over n, this actually scales as sigma over n. This is called the Heisenberg limit and so on. But we will not go into that. All I'm saying is like it really depends on what are the questions you're asking. So it's not a question of how far you can go, but it's a question of how are you going there? Like what is the scaling? That's the kind of question. Does it answer your question?
Yes.
Yeah. Okay. So basically, like now the question is like we are making it more sophisticated. So we are basically saying that you are measuring X such data points and Y such data points, and you are constructing a function set. So I know everything about X and Y, as in I know like they are coming from a distribution. Most probably, like most experimental cases, for very reasonable reasons, if you choose Gaussian noise for continuous variable or Gaussian fluctuation, that's a very reasonable assumption. So suppose X and Y are some Gaussian or some distribution which has a first moment, a second moment, and higher order moments and so on. Can I say anything about Z? Exactly in the same spirit I was doing before. We tried to say about this combined sums and means and so on. Now you have a complex function. What do? You always rely kind of on Taylor series that, like if you have already the mean, and if you assume that the distribution of X and Y, they're very not very noisy. You have designed an experiment, so the fluctuations are kind of small, so they are around the mean value. The system is fluctuating around the mean value. So you can expand, you can do a Taylor series expansion of this function, whatever it is. So any function, it doesn't matter what the functional form is. Around the minima or maxima, it looks very similar, and that's kind of the spirit you use. So this is basically the value around the mean, and then you expand. You keep the first term and the second term, and this fx is basically just del x of f, and similarly fxx is a del 2 del x square of f, the second derivative, the usual Taylor series. So now you are actually, this is z, and you are actually just interested in the first moment and the second moment, like the mean and the variance, because you have all this powerful central limit theorem now in your hand. You know that, no matter what this x and y distributions are, you can always make n large enough and make z distribution look like Gaussian. If it's Gaussian, only the first and the second moment will matter, So that is those are the ones I'm interested in, right? So I can calculate z, and z square, and once I calculate z and z square, I can actually calculate the variance of z square minus z. So this is, you can actually calculate this thing. So you see that if you put the averages here, this, of course, this average doesn't, this is not a random quantity. This is evaluated at mu x mu y. The second quantity, the average happens on this random variable x, and you see that this average x minus mu x is 0. And the same is y minus mu y. These are random variables centered around mu x and mu y. So you are basically left, when you're calculating z average, you're left with only x minus mu x square. And similarly, you can take the z square average, it's just like very simple algebra, just keep the terms properly. But when you do that properly, you're just left with, when you calculate z square minus z average square, you're left with quantities like this, del f del y, del x del y, del f del x del f del y, and this like del x del y of f, and then sigma x square, sigma y square, sigma x square, sigma y square. So exactly this combination is what you're left with. You do further approximation. Remember that you're already riding on the central limit theorem, so large n limits and so on. You do further approximation. You say that, as I was saying, that we are like, I have done a good with my experiment. So my variance, sigma x, sigma y, my parent distributions are smaller compared to the mean. They're small enough. So sigma x square, sigma y square are very small. So this kind of cross terms we can ignore. And when you do all that, you are basically find an expression for the error or the variance of this derived quantity z, which is actually derivative of that functional form. So this is del x whole square, del y whole square. Sorry, there is a whole square. I missed that. So this is square, sigma x square and sigma y square, and that is the very well-known what is called this error propagation formula, which basically says that it doesn't need to be just limited to one, just two variables. You can actually combine them to say that if for any functional form, so you have v equals I yard, or some very nasty things like you're trying to calculate, for example, what is it like? So, for example, like this guy in Olympics, he has thrown a javelin, and you're trying to calculate the range of this projectile, and what kind of variation in the angle will create what kind of variation in the range, whether you get to like 87 meters or whether person is throwing the javelin, sine theta is a random variable depending on his posture and so on, g is not. So all these random variables kind of combine, they have their own fluctuations, and you're asking, finally, what is the fluctuation in range? How much it's varying. These are very important quantities. So if you have that kind of functional relationship, you take the derivatives, and then you interestingly see that the final error, this goes back to that AI square, sigma square I was saying, that it's actually some weighted sum of the independent errors, and they're the square of the weighted sums. So any questions up to this point? So this is the most important thing. That's what I really wanted to talk about today. That this is what is famously known as the error propagation formula. This is actually the fact that if you know measurement of your independent errors, you might be measuring your voltage fluctuation or some current fluctuations. From there, you're inferring about some electric field, or even further, like some wavelength or some refractive index. So each of those errors add with the weight of the corresponding theory that tells you what that functional relationship is. So this is so important that there's a statement, very popular statement in the experimental community. They call it that errors add in quadrature, as in like errors. Remember that, like, this is what you will hear in a good lab always. And remember that errors add in quadrature, as in, like it's actually the square of the errors. That's what adds. So what that means is that suppose you are measuring two things, for example, you are measuring the current and the resistance to infer about the voltage. And finally, you are going to state that this is the measured voltage, 2 voltage plus minus 0.2 volts. So this plus minus 0.2, which is square of that, is actually a square of the error in the resistance and square of the error in the current, right? So now suppose your resistance, the company has given you a resistor which has like a 10% error, and you are measuring like a 1 milliamp current with a precision of 1 microamp, so 1 part in 1,000. And still, like students, who are not understanding this error propagation formula, they'll keep trying to record like, last 2 decimal places of this microampere current, whereas they're not realizing they're trying to improve like some 1%, which will eventually get square, 1% error, whereas the resistance already has 10% error. So your final error in voltage will be dominated by, the resistance error and not really this current error. So don't try to improve anything that's already good. Try to improve, try to identify what is the worst one, because they add quadratically, so small numbers, so the worst one will actually have the largest effect, and try to reduce that. Any questions? If not, just another point that often many places people will actually forget, because of primarily of the calipers and so on, people often state this kind of errors, so where is it? When you're calculating these averages, so people will often do this average and stop at the first expansion, and they often mistake. Actually, this is some historically this kind of error propagation formula have been propagating in books and so on for like many decades now. Even in net and many exams, actually people said these questions, but actually you only truncate the thing up to first place, and you take the averages, and you kind of say that, oh, this average is some sort of a mean error, or I don't know, like maximum error, minimum error, some strange bizarre logic. But any random variable about its mean, the average should be 0. So people actually have this wrong approach where they'll say that now Z minus this Z naught, this del Z is basically this first terms in this thing. So actually, so this is what they'll state. They'll put everywhere this mod signs, and they'll say this is your error. So this is wrong. This just doesn't exist because of the fact that this average is equal to 0. So that's basically one thing to remember, that this is the right form and not the other one. Yeah. I think this is all I have to say. If there are questions, we can take more questions.
Okay, so if anybody has any question, just unmute yourself and just speak up.
So maybe I'll just put the initial first 2 parts. This case 1 and case 2. Any questions? Nothing? So I'll then send that PDF and this notes.
Okay, just email it to me and then I'll put it on the.
Yeah, I'll just email it to you and then you can just upload it.
Yeah. Okay,
yeah,
so
Saikat, I just wanted to make a point. That, for example, they are doing an experiment and they are measuring with a light meters various values, So for the setting up of a particular parameter, for one setting or one position, one location, or one condition of the instrument, they will measure a set of data. And that is what they have to relate to this, where
Exactly.
individual data is going to be like the mean of that and its distribution, which will give it some kind of distribution. And that is to be done for different settings. And from there, over and above, you have to go and figure out the Z, f of x, right?
Exactly.
So
Yeah, so basically this is the simplest case, like where you can take just one data point, but they can of course improve with many data points. And often I think in your case also you will have this, no, in this course. So like some sort of an image, you know, where there are this fringe kind of values, and then you basically maybe, you know, like one will have this kind of interference fringe and actually takes it in a camera. So if you actually if they actually kind of enlarge this, we'll actually find eventually pixels. Right. And you will find that what we call this line, now here this line, we are calling this the maximum, you know, so this intensity may be going as some sine square phi over 2, you know, but actually there's a delta of this. Because we'll basically find that, you know, if I take a cross section of this line, I'll basically find that that intensity has a sine square shape, but around that it's fluctuating. Correct. So if they do this pixel analysis, they'll see it there also.
Yeah.
Yeah, that's a very good point.
Okay, so this is last chance. Any question anybody has? Feel free. Okay, so I think we'll thank Saikat for these 2 fantastic lectures. And again, the resources that he sends us, I'll put that on the website so that everybody has kind of access to that. So thank you so much, Saikat.
Thank you.